As you work through the interpretation of a derivative as a coefficient of first-order variation, what matters is that you can recognize derivatives in whatever form they appear. Let's look at a few examples. Consider springs that you have maybe learned about in your physics class. One of the things that you probably learned was that if you have a spring that's near equilibrium and you look at the relationship between force and displacement, then that's a linear relationship. And there's this constant, this spring constant that tells you the relationship between force and displacement. That's Hooke's law. Okay, so that's what you learned in physics class, but the truth is, springs are not linear. Springs are nonlinear. You can have hard springs, soft springs, all kinds of things. But if you look near equilibrium, that relationship between force and displacement is really close to a linear relationship. And that coefficient of first-order variation is the spring constant. It's the derivative of the force with respect to the displacement. That's really what Hooke's law is all about. It's a derivative. That's what the spring constant is. Well, let's move on from physics to economics, where one often reasons about systems at the margin. Let's say that you're looking at a function of sales. Maybe it's revenue, or maybe it's profit. If you want to talk about what is happening near a particular sales level, one considers the marginal revenue or the marginal profit as being a coefficient of first-order variation. If you increase your sales by a little bit, how does the revenue change? How does the profit change? Now, in econ class, this often gets stated as, if you sell one additional unit, what's the increase in revenue or profit? But really, we could just think about changing the amount of sales, either positive or negative, by some small amount. What is the coefficient of first-order variation? These marginal quantities are really derivatives. What else is a derivative? Consider a chemical reaction. The reaction rate of a component, C, is the derivative of the concentration of C with respect to time. If you change time a little bit, how does the concentration change? That's a coefficient of first-order variation. That is what a reaction rate is. Now, there's so much more out there that is really a coefficient of first-order variation. You already know about velocity, about acceleration of a moving body? Sure. What about current as a rate of change of charge with respect to time? What about more exotic things like the elastic modulus of a solid body or the viscosity of a fluid? All of these things are really derivatives. They're really just coefficients of first-order variation. This is how it's always been, and now you understand this interpretation of derivatives.